Okay, we're ready to do lesson 3. So we've been doing concurrent force systems. We did 2D concurrent force systems, and we did 3D concurrent force systems. And that's all the material that we'll do just on concurrent force systems, but they'll keep showing up in several more of the individual classes from here on out. So if you have questions about them, I'm looking at the poll. There's only like 3 or 4 answers to the poll. Before 4 people answered the poll, so it's not a huge sample size, but it looks like most people are at least getting there with concurrent forces. But if you do end up with some questions, then put them in the chat or Discord or email or whatever, so that we can make sure that that part of it is understood, because it does become a foundation for a lot of the things that we'll do for the rest of the course. Today we're doing something different. It's still concurrent forces, but we're going to use them in a different way today. So what we're doing today is what I'm going to classify as axial stress. So let's see if we can scroll it where it's not under my picture there. There we go. Axial stresses. So the axial word is important. The stress word is important. Then we've got this normal, shearing, and bearing. And by the end of today, hopefully all of those words mean something. And in the context of mechanics of materials. So we're still in the statics part, so we're not talking about things that have dynamic forces applied to them, and they're moving around or whatever. So it's still a static situation, static equilibrium, but now these forces are doing stuff to the object they're applied to. So they're trying to stretch it out or make it compress, or maybe they're making it try to shear, which we'll talk about what that word means. Or they're pressing on it, whatever. So they're actually doing stuff, and the material is responding in certain ways. And that's what we want to start getting into. That's the mechanics of materials part of this class. So I think for first, let's go over here and let's start talking about what some of these things mean. So we're going to have axial stress. So let's work on axial first. Let me move this closer. All right, so axial. What we're talking about with axial, we're usually referring to an axial force creating an axial stress. And so the axial part means that for the most part, the objects that we're dealing with have some sort of longitudinal axis. So if you had like a little, well, let's do a simple one. You had like a rope. Well, this is more like a rod, I guess, because I'm not going to draw a rope. It definitely has a longitudinal axis like that, right? So definitely has an axis. It doesn't have to be a longitudinal axis, but it makes more sense for what we're doing most of the time. So longitudinal axis. And the axial force would be on that axis. So we could have a force over here, and we need an opposing force over here. If we don't have this opposing force and they're the same value, I'll just call them F. If those forces aren't opposed, then I'm not in static equilibrium anymore, because I apply a force to something and it's imbalanced. It's not in equilibrium, then that something is moving, and I'm not in static anymore. So this force that I've drawn, or these forces that I've drawn, these are the axial forces. So they are lined up with this axis that I've identified, and they're both on that same axis, and so they're axial forces. These axial forces can create all these stresses that we're interested in. So let's talk about stress. So stress, maybe if we look at the units of stress, that'll help us understand what it is. But if we were going to define it, I would call it the intensity of internal, so this word is important, internal forces. So the F vector that I drew on the previous picture, those are external forces. They're applied to the little rod we drew. The internal forces are what's happening inside the rod as a result of these external forces. So what we usually have to do is, in order to see what's going on inside the object, we need to cut it open. So I'll do something like, let's draw a green line. You know, that'll be our cut line. And I'll cut open, you know, figuratively. I'll imagine I may even draw the cut open rod, and it'll look something. I'm going to draw the left-hand side. It doesn't matter which side I draw. I can get the same information, but I'm going to draw the left-hand side in this case. So there's the left-hand side of the little rod. I've cut it open. I know that over here I have an external force, or maybe you might hear it as an applied force. And it's axial. It is an axial, external, or applied force. And for this little piece to be in equilibrium, I need to have this external force balanced out. Right? Because if I look at this free body diagram that I have on the screen right here, the second one, then that piece is accelerating off to the left of the screen, which would mean it's coming apart from the rod, because the rod is not accelerating. If I look at the whole rod, then it's balanced, it's in equilibrium, and it's just sitting there being stretched. But this left-hand side, if I draw the free body diagram this way, then it's actually accelerating off to the left. So I know that's not true. So what I have to do is I have to say, well, there must be some internal force over here that is balancing out that external force. And if I think about one of my equilibrium equations, the summation of forces in the x direction equals 0, or else the body, the free body diagram body, is not in equilibrium. By the way, this little partial piece is a free body diagram. You don't have to draw an entire body. It can be a piece of a body, one body, or multiple bodies all put together. So this is, in this case, we're a piece of a body. And if I look at it, my equilibrium equation says that, well, in order for this thing to be in equilibrium, this internal force has to equal F. Otherwise, they're not balanced. And the little piece that I've drawn is moving away from the rest of the body. And that's not happening. So this is one of the common hurdles to jump over when you first start doing this. Because if you look at the first free body diagram that I drew with both F forces on it, the first one before I cut it apart, a lot of people, probably even most people, will look at that and say that, all right, I've got, let's say that F is 10 pounds. I've got 10 pounds pulling to the left, and I've got 10 pounds pulling to the right. So inside this thing, there must be 20 pounds. 10 going one way and 10 going the other way must create 20 inside it. And most people, in the 20 years that I've been teaching this concept, most people seem to think that that's true. But when you look at it, and you actually cut the body open, and so we're going to draw a lot of these little, they're going to get very simple, hopefully, to you, but we're going to draw them even when they're simple, like the one that we drew here where we cut it open, just to make sure that we reinforce the point that you cut it open, draw the free body diagram, and it turns out that internal force, I probably shouldn't have called it F, but it does have to equal F. So this is the internal force. It is only F in 10 pounds, in my example. So it's not 20 pounds inside there. It's not 2F. It's just 1F opposing that external force. So that's a thing that most people, when the first time they see it, are going to have to not do the intuitive thing. Actually draw the picture and figure it out, and figure out that, oh no, the internal force is only F in this case. All right. Back to stress. So stress is the intensity of internal forces. So there's the internal force in our picture. It's the one going to the right. How I get to the intensity part is this force F is spread out over that internal cross-sectional area. Now, maybe I should redraw it a little bit. So I drew this as a rod, a circular rod. So, when I drew the free body diagram the first time, I kind of drew it as a little zigzag, showing that we cut it open. But let's draw it as a circle. So there, we'll use green. That little surface is the area, the surface area. Well, I guess it's not a surface technically, but we cut it open in our picture, so it became a surface. But it's the cross-sectional area is what would be a better word. So that cross-sectional area is where this internal force F acts. So it acts on that area. And to get the idea of intensity, how I actually calculate stress, stress is equal to force divided by the area that it's acting on. So the whatever force we're talking about, in this case that internal force F, is spread out over this area that I shaded green. And if I know those two values, if I know force is 10 pounds and that cross-sectional area is 2 square inches, then I calculate it. 10 pounds divided by 2 square inches is 5 pounds per square inch, or 5 psi. And I can actually calculate the stress at that point. The axial, I'm going to use, let's see, how many words? Maybe 3 different words for it. It will sometimes be referred to as axial stress. Sometimes it'll be referred to as normal stress. This normal is not like average. This normal is perpendicular. And what it means is perpendicular is the force is perpendicular to that area. Got a lot of letters there. Not cross-sectional area. Okay. There might be, I don't know if I'll refer to it in any other way. Probably just these two, axial stress and normal stress. If I think of another way I refer to it, then I'll throw that one in there too. But most of the time it's going to be one of these two. Normal stress, meaning that it's a stress created by a force on a perpendicular area, or maybe just called axial stress. Sometimes some people might call it axial normal stress. All right, so let's do a little bit of calculation with that. So we kind of did one here. We didn't put any numbers onto it. Let's make our system slightly more complicated. Not very complicated, but a little more. And let's say that we have this setup. I'm going to draw it sort of in an isometric view, just so we have a little idea of 3D. I guess this isn't necessarily isometric, but it's close enough for what we're doing. So what I've got here is a little plate that we're going to put axial force on. So something like that. And we're going to put, this will be a tensile force. So tensile forces pull things apart and put them in tension. And let's put some numbers. Let's say that this is 300 pounds. And so for our little block, to be in equilibrium, then I have to be pulling in the other direction also with 300 pounds. You know, it could be that the other end of this block is attached, welded to a wall or whatever. Maybe that's what is holding it back. That still represents 300 pounds of attachment force. Let's put some dimensions. And let's say that this dimension, I don't know, let's make that 1/2 inch. Let's make this dimension, let's make it 2 inches. Let's say that this block itself is made from kind of a generic name here, structural steel. So it does matter what the material is. It doesn't matter as far as calculating the stress, but how the material, how the block responds obviously matters on what the material is. If I put 300 pounds on a 2 by 1/2 inch piece of steel, that's going to have a different response from 300 pounds on a 2 by 1/2 inch block of chocolate. You know, they're going to behave very differently. So the material does matter on the response, but the stress calculation is the same either way. So let's do the extra step, which hopefully eventually we won't need to do this step, but for now let's do this extra step of cutting the block open so that we can see the internal forces. When you're doing this, you generally want to cut the block somewhere near the middle, so maybe like over here. If you cut too close to the ends, then it might get confusing on where forces are applied. So just go to the middle and cut it open. And then pick one of these free body diagrams to draw. So I will do this. If I can get my cursor in the right spot. There we go. Oh, all right. That's fine. And then we cut open, I'll draw it a little bit jaggedy. If this were a real broken piece of metal, then it wouldn't break perfectly straight across there. So even though we're using these diagrams to try and figure out what's going to happen to the material, we're not being super realistic about what kind of shape is it going to break or deform into. There's a lot more that happens in reality than what we'll get to in this. Like, this is the intro level course. It gets a lot more complicated later on. For now, let's just assume things break in nice flat planes and surfaces, like kind of what I've drawn here. So I don't really have, maybe that 300 pounds is in the X direction. You know, I could make the axis that way. And I could apply my summation of forces in the X direction, have to add a 0 equilibrium equation, which would tell me that this internal force must be 300 pounds. Now, I already knew that based on what we did earlier with our rod up here, but sometimes it does help to draw it in the beginning. In general, it's usually good to draw your free body diagrams even when they're simple like this. I would say there was a question, maybe not in the chat, but there was a question about how do you get better at drawing free body diagrams? And I would say this is how you get better. You draw the ones that are obvious because they're good practice and you should be able to get them right. And the more times you draw them, the more it becomes a pattern of, oh, I have to identify an object. Oh, I have to identify the forces. I have to identify what kind of forces they are and where they're applied. And I've got to put in a coordinate. You know, you get in the habit of remembering all the steps on the simple stuff. And that helps. Those steps really help on the more complicated things, remembering to do all the little steps. So draw the simple ones just as practice, even though you already know there's 300 pounds of internal force here. All right. It wouldn't hurt for us to put our dimensions on here. just so that we have them. They're right up above there, but doesn't hurt to go ahead and put them on here too. This surface here, that's our cross-sectional area that the internal force 300 pounds is applied to. And our stress equation, I'm going to put axial stress up here, is internal force divided by cross-sectional area that it's applied to. Now we have variables for these. I'm writing out words. So most of the time I'm not going to write out words. I'm going to write variables, and I'm going to use sigma. That's my lowercase sigma. And that's going to represent normal stress or axial stress. And force is going to be F or P sometimes, or maybe even T if it's a tension. I will use F for now. And A for area, cross-sectional area. So the equation will more than often look like this: sigma equals F over A. Sometimes you'll see sigma equals P over A, but a lot of times you'll see F over A. So now plugging in our actual numbers, F, the internal force, 300 pounds. Area, the little blue cross-sectional area, 2 inches times 1/2 inch. So calculating that math, 300 pounds per inch squared, and a lot of times 300 PSI, pounds per inch squared. So now we know, the axial stress is 300 PSI. We don't really know what that means, but we know that the number is 300 PSI. So to know what it means, we have to look up something with the structural steel. So you need to go to our book. My book's kind of dirty on these pages, so we'll have to deal with it. Let's get down there. This is page 704 in the textbook we're using. There are also some of these scans of these pages in Moodle. Right here is structural steel. Let's see if we can get close enough where we can actually read the numbers. Kind of. All right, so right there is structural steel. And then across the top, I've got a lot of different columns. So I've got specific weight, that's like density. I've got 3 columns called elastic strength, tension, compression, shear. And I've got 3 more: ultimate strength, tension, compression, shear. Got something called the endurance limit, and I've got these 2 modulus numbers, and then a thermal expansion number. So what we're dealing with our little block with the 300 pounds on it, the most likely form of failure, like this might be a block that's in some kind of machine somewhere, and it's got to hold something in place, but it's being pulled on by 300 pounds, so it would fail potentially. If this machine is moving around, this part stretching out could cause the machine to fail. Like it gets out of tolerance and parts don't move the way they're supposed to. So that kind of failure would be under the elastic column. So the elastic strength would be something stretched too much. The ultimate strength would be even worse. So ultimate strength would be it fractured, it came apart, broke in half. But usually just stretching too much, like an elastic band, is also going to be failures. And it's a lower number. It's easier to stretch something than it is to fracture it. So I'm going to look under the elastic set of numbers. And then I've got numbers for tension. I've got a letter for compression. I don't have anything for shear. So our little setup, let's go back to our picture here. Uh-oh, did we lose our picture? Let me see why we lost. Not sure why we lost our picture. Oh, did I close it? I might have closed it. No, there it is. There it is. I just minimized it. All right. our little picture has the arrows. The internal arrow is pointing away from the area that it's applied to, and that's a sign that it's in tension. So compression would be the arrows pointing towards the thing, pushing on it. Shear is a totally different thing, and we'll talk about shear later on. So back to our book, I've got tension with a number, 36, and then the units are up here, KSI. So back to our writing over here. KSI is a weird unit. So we've been using US units here, pounds and inches and things like that. But there also are metric units, millimeters, inches, things like that. And the metric system has all of the prefixes like milli and kilo and mega and giga and all those kind of things. Well, KSI is a weird thing that combines the US customary units with the prefixes from the metric system. So KSI takes the K from kilo and says that, oh, a KSI is 1,000 PSI. So our little number, 300 PSI, that would equal 0.3 KSI. So not very many. We do this because the strengths of most materials, engineering materials, are really pretty high in PSI, like, tens of thousands of PSI or more. And so it's just easier to deal with. Instead of 523 PSI, it's easier to use 36 KSI, just to write it and deal with it and average out kind of the decimals and all that kind of stuff. So let's go back to our book and look at what we have over here. We have structural steel. It's off the page, off the page. Tensile elastic strength of 36 KSI. So let's write that on our deal over here. That elastic strength is also called the yield strength. Yielding in the sense that it is the point where the material, in this case the structural steel, begins to yield, which means that it begins to stretch to the point that it will never go back to its original shape without like forcing it to. It won't just snap back. And I'll usually say sigma y is the yield strength. Sigma y equals yield strength is the same thing as what your book is calling elastic strength. So sigma y, the yield strength for structural steel, is 36 KSI, which equals 36,000 PSI. We have applied, oh, it's off the screen a little bit. There we go. We have applied 0.3 KSI. And it has to get to 36,000. It has to get over 36 KSI, 36,000 PSI, before it even begins to yield. So we are nowhere near yielding this little block of metal. We could make it much, much smaller and still have plenty of room to add more force or whatever. What we have done here is we have created what's called a factor of safety. So, and you will normally want that. You'll want a factor of safety applied to your design, because it could be that you design something, you design this little block that we have, and you design it for this exact use case where it's got 300 pounds here, 300 pounds here, but when somebody goes and uses the thing, puts it into service, there's some other forces on it, or maybe the force is higher than 300 pounds, or maybe there's a force that's causing it to bend, or it's doing something that you didn't actually design for. Then that factor of safety that you've built in will help it to where in case something unexpected happens to the part you design, it's still safe. So we have a huge factor of safety. We have a factor of safety equal to factor of safety equals our yield strength. I'm going to call that our allowable stress. So sigma allowable divided by our actual stress, sigma. And our sigma allowable, we're just saying that we don't want it to yield. So our sigma allowable is 36 KSI, and we have 0.3 KSI. So if I divide 36 divided by 0.3, I get 120. I have a factor of safety of 120. Normally your factors of safety in engineering design are around 2, something like that. And we have 120. So we have way more room to add more force or to redesign our part to make it smaller and lightweight or whatever. So that's kind of the general process for calculating an axial stress. I don't see any questions popping up, so I think we're okay there. Let's stay on axial stress, but make it like one level more difficult, but still not very hard. All right, so let's just take the same thing. So take that. And let's just add to it that, well, we do have a lot of factor of safety. I want this to be lighter weight, so I'm going to drill a hole in the middle of it. And I'm going to make the hole, let's see, I have a 2-inch. I'm going to make this 1-inch diameter. That little symbol means diameter. So I've drilled a 1-inch hole in the middle of this to make my part lighter. I don't need all the strength that it has. So I would rather, it's a machine. Usually machines work better if the parts they're moving around are lighter, but still as strong as they need to be. So I drilled a hole in the middle of it. And now my free body diagram looks similar to this, but now I know that I did weaken the part by drilling a hole in it. I know there's less material exactly where I still have this cut line. So if I had put the hole somewhere else, then I might need to move where I cut the part of open at, because I intuitively know that, well, there's a big hole there, so that's the weaker spot. So when I draw the free body diagram now, it looks like this. It still has 300 pounds over here. I'm going to make some assumptions that our little cross sections that are holding it together, here and here, before that went all the way across, right? But now there's a hole in there that's don't have as much material. I'm going to make the assumption that everything's kind of centered up, and 150 pounds is over here, and the other 150 is over here. So I still have a total of 300 pounds, so the part's in equilibrium, but I've just split it up a little bit. So now when I go to do the same thing, sigma equals F over A, I have, well, there's 2 internal forces, so I'll add those together. There are 2 areas. I didn't mention them, did I? So this I had at 1/2 inch. I said, I didn't label it out, but I said that the hole was centered, and it's a 1-inch diameter hole. So this little part ends up 1/2 inch, and this little part ends up 1/2 inch. So they're exactly the same. So I have 2 areas that are each 1/2 inch thick by 1/2 inch wide. So this is my new equation. So now when I plug the numbers in, I get 300 total pounds of internal force spread out over 0.5 times 0.5 times 2, half a square inch of area, and my new stress, 300 divided by 0.5, is 600 psi, or 0.6 ksi. Still way below the threshold for yielding this material. But now my factor of safety is only 60, which is still way more than it needs to be. But this would be an example of the part doesn't have this nice straight cross section. I'm looking for, well, where is the weakest spot? As far as we're concerned, the weakest spot is the cross section that is the smallest. So wherever you have the most force applied to the smallest cross section, then that's the one that's likely to fail first. So in this case, the weakest cross section is right through the middle of the hole, and I've got these two little cross sections supporting the 300 pounds. So there'll be some problems like that. This one, is still on the simple side. It's there will be stuff like this on exam 1, and this is kind of the fundamental level. Maybe like if I were rating them out of 5, this might be a 2 out of 5 difficulty. This one would be a 1. This one might be a 2. All right, so I think that gets us all we need to know about axial normal stress for the time being. Don't see any questions. The next one I wrote down was shear stress. All right. Do I want to do shear? Let's actually do bearing stress next. On the little Moodle page, I have it listed shear a second, but it's a different time altogether. So let's do bearing stress. All right, so could we see a 4? Oh, yeah. So the 4s and 5s, those are in the web work. And so what I do with those is if there's a particular one that's given trouble and I get questions about it, then I'll generally work that one in web on the stream so that you can kind of see how the more difficult ones. But most of the, not all, but many of the web work are at the 4 and 5 level, certainly the 3 level. And there might be a few that are the 1 and 2 level. So if there's one that you've run across in web work that is, people are struggling with, let me know and I'll pull it up and we'll work through that. And those are usually more on the 4 and 5 level. All right, so bearing stress. Bearing stress is similar to the normal stress because it sometimes does show up as a normal force, but the bearing word here, it means, let's see. The simplest way I could put it, most generic way I think, is one surface bearing, so pressing, on another surface. So that's the simplest definition for bearing stress. So it does end up often looking like a compressive normal stress, but we call it bearing stress. And there's another kind that we'll talk about after this that is bearing stress that doesn't really look like what we just did. So let's do the one that looks like what we just did. And I don't know, maybe you've jacked up a car at some point, or you've built a scaffold or something where it's got this small leg and it kept sinking into the ground. And to stop doing that, you put a piece of metal or a piece of wood under that leg so it wouldn't sink down into the ground. So what you did is you increased the surface area. So the little leg that was on the ground has a small surface area and it kept poking down in the ground. Stress was too high. You spread out that force over a larger plate, maybe like a stand or whatever, and it didn't sink into the ground as much or at all anymore. So what you did is you changed the bearing stress between the leg and the ground by spreading it out more. So let's just have really straightforward one. This is going to be a side view. Here's a side view. There's the ground. These little cross hatch marks that I'm showing here, hatch marks, whenever I draw those, that means that whatever I'm drawing is stationary. It's not moving somewhere. So let's say that we've got a piece of wood here, and we have put a chair leg or some kind of leg on it, and whatever that is pushing down with 200 pounds. So if we don't put this little block under there, that 200 pounds gets applied to the ground in a really small area, however big the chair leg is. But when we spread it out, that area becomes, I don't know, maybe we can draw, I don't know, let's see. There's our little block, you know, and it's spread out over the ground. There's the chair leg. There's the 200 pounds. So instead of the 200 pounds being spread over that little area, it's spread out over this whole area here, which is way bigger. And if we have essentially the same equation, but we made A bigger, A's in the denominator, that means sigma, the stress, went down. It got smaller. So bearing stress is really simple to calculate when it's something like this. Just one thing pushing on another one. They're both flat. You just calculate the area between them, and that's the bearing area. It does get a little bit more complicated if we have maybe a plate like this one that has a hole in it, but that hole is so that a pin or a bolt or a rod can go through the hole and push on the side of that hole. So let's draw a side view of what that might look like. Let's say that you've got a plate here, and then you've got another one that overlaps it, and they're being pulled apart. Now you'll notice that these forces aren't exactly axial. That's fine. We're not getting too caught up in the exact details of what would really happen. It's going to be close enough. So these are not welded together, they're bolted together. So I've drilled a hole through both of these plates, and I have put a pin, or a bolt I said, didn't I? In that hole. Comes out the other side. There's a nut over there. You know, there's some threads. All that kind of stuff. So when I try to pull these plates apart, the bolt in there, it's clamping them down. Let's say that it's loose and it's not actually clamping too tight. But what's happening is this shaft of the bolt, the shank of the bolt, is pressing on the inside surface of these plates. And so it's pressing one surface, pressing on another surface. So it is a bearing stress, but it's curved. So how we might do that is, let's look at the bottom plate. And I'm going to draw this free body diagram right there. I'm going to draw that. I'm going to draw it in 3D, sort of. Okay, so something like that would be if I took that little part I circled in green and drew it in 3D. The plate is being pulled this way. I didn't put numbers on that. Let's use 400 pounds this time. So 200 pounds here, 200 pounds here. How it's not moving, because this free body diagram would be moving to the right, correct? How it's not moving is the inside surface of this hole is pressing against the bolt, you know, right there. And that's a bearing stress. It's just on a curved surface. So The problem with that is if I look at the actual stress distribution. So now we're going to look at this. So this is kind of the ISO view. Let's look at a top view over here of the same thing. So here's my 200 pounds. And I have a total of 200 pounds pushing back here, but it doesn't all push right there. It kind of like there's a tiny bit here, a little more here, a little more here, a little more here, maximum in the middle, and then it fades out again. And so it's not evenly distributed on that. But the total of it is 200 pounds. But since it's this weird like distribution, how we normally model that is we use what's called a projected area. And so I will go in and take that little free body diagram, take the curved surface, and I will project it on to a flat surface, just like that one. And use that as the area. So in this case, the projected area, I didn't put dimensions. Let's use our same 1/2 inch plate. And let's make that the same hole that was 1 inch. That's going to be, we'll do it up here. And so the projected area would be 1 inch times 1/2 inch. So it'd be 1/2 inch squared. And then I could force 200 pounds. Oh, I guess I didn't draw the actual force. So there would be the 200 pounds applied. Oh, wait. 400 pounds. Sorry. Not 4,000. 400 pounds applied to that projected area. So 400 divided by 1/2 inch squared, 800 psi. On the inner surface of that bolt hole is what I would be looking at there. So that's the two types of bearing stress. One where there's just, kind of a rectangular area that's between contact surface between two objects. That one's pretty straightforward. And then this one where it's a curved surface, like a pin inside a hole or a bolt inside a hole, something like that. And we use the projected area. Okay, so that's bearing stress. The last one we're going to do is going to be, it's actually, we're going to divide it into two categories, but they both are called shear stress. Okay, so if we go back to our book, I had a column here for shear. I have a column for compression. So tension and compression are the same thing, except when we're looking at our free body diagrams, the arrows are pulling away from the body. If it's tension, this 400 pounds on the projected area, that's pushing towards the body, that's compression. So some materials have different strengths in compression and tension. Many materials have the same though, and that's what this B means. If you go to the footnotes down here, if I can get to them, right there. B for ductile metals, which are most of the metals you design most machines with. It is customary to assume the properties in compression have the same values as those in tension. So that's what the little B symbol means on most of the ones. Here's some. Let's see. There's one. 14 and... Oh, well, actually, they're the same. Here's one that's different. 132 in tension, 145 in compression. That's a heat-treated steel. All right, so that's what that is. But shear is totally missing on a lot of these. There are a couple that have a number in shear. The reason that shear is not listed here is it will, assuming you keep taking classes in mechanics, strength of materials stuff, then you'll have the option of a whole bunch of different ways to model that value for shear. And so that's why they leave it blank, is because they don't really know Are you going to use distortion energy, maximum shear? What are you going to use to model that value? What we're going to do is super easy, and it's super conservative. So the other methods are a little more accurate, but they are not as conservative, meaning that they're good. They're good to use, but they are, I guess I would say, more an expert level. You have to know that you can really apply that model to your situation. So we're going to say that we're just learning right now, and we don't know all the different scenarios. So we're going to take the most conservative approach, which is just take your tension number, 36, and divide it by 2. So shear will be 18 for us. The shear strength in an elastic yield setup. So just take, if it's not listed, which most are not, take the tensile number that you're dealing with and divide it by 2. So that's what we're going to do for shear strength. Okay. Now, shear is the same idea. It's still a force divided by an area, but there's one big difference. Shear stress equals internal force and last time we used a F or a P for the internal force when we were talking about the normal stress. Here we usually use the letter V for saying it's a shear force. And it's divided by some kind of area. And we'll still use A for that. The big difference is this, though. Where'd I write it? So the normal stress, the force and area were perpendicular, and the shear stress, they are not. In fact, for everything that we do, they're parallel. So if you ever draw a free body diagram and the force that you're looking at is actually parallel to the surface that it's acting on, now you know you've got a shear stress. And it's important because the strengths are so different. If you thought you had a normal stress with a strength of 36 ksi, but you really had a shear stress with a strength of 18 ksi, that's a big difference. So you do have to make sure that you keep shear stress separate from bearing stress and normal stress. All right. Let's do 2 examples of what shear stress can look like, 2 different cases. And I think that will, assuming there's no questions we need to sort out, I think that'll get us done for today. I'll open up homework, I guess 3 for web work. I believe our first homework 1 in web work is coming due tomorrow because once they open, they're open for a week. And so homework 1 is getting very close to being done. It's just like resultants, things like that. Oh, there's one question, homework 1, problem 7. We'll look at that once we are done with the shear stress. All right, so one case for shear stress. Let's go back to this idea here. In fact, let's copy that. Wow, I don't know what that was. So, let me try that again. That looks better. Okay, so we thought we've done 2 modes of failure, right? We did a plate that had a hole in it. We calculated how that might fail. we did maybe the bearing stress on this hole gets too large and it deforms the hole, and so now the joint is loose and wobbly. That could be a failure mode. If neither of those happen, another thing that could happen is it could just break right here. Like the bolt could break. So if we draw that free, I'm going to draw the bottom picture. So if I draw the bottom free body diagram, I've got the plate. It's got its 400 pounds of force on it. I have a hole drilled somewhere in there, and inside that hole is a bolt that failed. So the bolt's in there and it broke. So that surface area, if I make this bottom piece in equilibrium, there could be if I really crank down this bolt, there could be some friction between the top plate and the bottom plate. I'm ignoring that. That probably is true. There probably is some amount of friction that's helping hold them together. I'm assuming it's negligible, and most all of the work of holding top plate to bottom plate is done in this bolt. Then right on this surface is a force, 400 pounds, holding everything together. And notice I drew the arrow with only one side on it. When you draw it with one side, that represents a shear force. Also, just, I don't know, not super important, but the correct ratio of an arrowhead for technical drawing, I mean, that sounds kind of ridiculous, but there is actually a 3:1 ratio for the arrowhead, if you ever wanted to know that. I don't know that I have mine exactly right there. I didn't measure, but there is a 3:1 ratio. If you were, like back in the old days, all the shop drawings and drawings for parts that were going to be, they were all drawn by hand. There was no computer out there drawing them, and they had to have a lot of different rules. In fact, one of the rules would be you don't put your dimensions on top of the thing you're drawing, which I just broke right there. So whatever. So going back to our shear force thing here, the shear force, the one with only half an arrowhead, is parallel. It's sitting right on top of where I think this bolt would break if the bolt itself broke. So that is a shear force. It's not perpendicular. So now I know of, the other thing that's different is instead of sigma, we use tau, lowercase tau, to represent shear stress. Tau equals V over A. V is the internal force, so the force applied to the area looks like it's 400 pounds. The area, did we ever specify anything about this area? It's a giant bolt, 1 inch diameter. Okay. So the area here is a pi d squared over 4. I know a lot of times, you learn circle area is pi r squared. That's easier to remember. Fewer things in there. Most of the time in engineering, you're going to use pi d squared over 4. They're the exact same number, but when you go to measure something, actually measure the width of something, you're measuring its diameter. Or when you're talking about a bolt, you're talking about its diameter. You're not saying the radius of the bolt, and you're not measuring the radius. So most of the time, you're going to be dealing in diameters, and so probably a good idea to get used to using pi d squared over 4 instead of pi r squared, just for the reason that you're normally talking about diameters and not radiuses, radii. All right, so let's see what this equals. I've got pi times 1 squared, so that's 1. Pi over 4 and I've got 400 divided by that, 509 psi. So still not a lot. Remember, if this is also a steel bolt, then the yield strength, elastic strength, is going to be in the 36,000 range. The shear strength is going to be around half that, so 18,000 psi, and I'm at 500 psi. So plenty of safety factor on that. One last thing that could happen to our bolted joint or pin joint. So if it doesn't fail this way, like breaking, fracturing across the hole, if it doesn't fail this way where it presses on the hole too much and distorts it somehow, and it doesn't fail this way where it breaks the bolt in half, one other thing that could happen could be, where's it? We may have to draw a new picture. Let's draw the bottom plate and show how the other thing that could happen. This is called tear out. So for the bottom plate to tear out would look like none of those other things happened, but this little piece of material behind the bolt tore out of the plate. So right there. And then trying to draw this one, dotted because it's on the inside that we can't see. So there's my 400-pound external load, and I've got a 200-pound shear stress here, and a matching one on this side. The little piece that came out looks like this, where this little area tore and the one back here also tore. I had a 400-pound force, bearing force, pushing that little piece out, and there's the 200-pound shear force there, and then there's one on this side as well. So those shear forces, the 200-pound ones, those are parallel to the little area, the tear out area. Sometimes this is also called punch out, but I'm usually going to call it tear out. And so that's a shear stress. Force is parallel to this area, so that's a shear stress. It's definitely not perpendicular. So I would have tau equals V over A. It doesn't matter which one of these I look at. If I look at the little piece that got torn out, or if I look at the block that's left, they'll both calculate the same way. Let's look at the little piece that tore out. I have a total shear force of 400 pounds. I have two that are each 200 pounds, so 400 pounds. The area is measured, I have to go up here. The area is measured from the center of the hole to the end of the block. We never made that dimension, so let's just say that that dimension is 3/4 of an inch. So that would be that dimension right there. So the area, again, I have two of them. I have one facing us and one on the back side of that little block that tore out. So two of them. Each one is 1/2 an inch long, and I already set somewhere, I already set the plate thickness at 1/2 an inch thick. So 3/4 of an inch long by 1/2 an inch thick. So now we have 0.75 times 0.5 times 2, 400 divided by that number, which is 0.75, 533.3 psi. So still, again, nowhere near the actual stress needed to fail the part, but still another potential way it could fail. You can use this same procedure tear out. That's the reason it's called punch out sometimes, is you could use it like you're making cookies. You've got a cookie cutter and you're punching out shapes. You can use it in that way too, because that would be the exact same thing. You're punching out some kind of shape. All right. So the question was homework 1, problem 7 from web work. Let's see if I can get in there, and then we'll look at it and see if it's someone I can do. Hopefully I can. Homework 1, problem 7. Oh, well, I can at least get it started for you. Let's see. Here's what it looks like. Oh, look, this one even has a rating on it. So difficulty 5 out of 5. I don't know if I would call this one 5 out of 5, but it is a difficult one because there's several things going on at the same time, and I think you have to solve it simultaneously. So this one is actually a good one that goes along with the other question of free body diagrams too, because this one's going to require multiple free body diagrams, I believe. So let's put down our dimensions. So yours are undoubtedly going to have different numbers than mine, but that's fine. Alpha 31 degrees, beta 59 degrees, A is a 101 pound weight, B is a 21 pound weight, so quite a bit different. Determine the tension in the cable and angle theta. All right, so the tension in cable AB and angle theta, where does it end up at? So what I would do with this one to get started is, when you draw a free body diagram, sometimes you have to draw ones just to get equations written because you don't know anything. But here we do have a couple of things that we know. We know the 101 pound and we know the 21 pound. So that gives me a clue that I can use those as a known value in a free body diagram. So let's just start with identifying this guy as our first body of interest. And I don't even know if this is the right way to solve it. I'm just going how I would start it. So I've identified ball A as my body of interest. So now I need to draw ball A. This is one of the cases, in a lot of times the concurrent force systems, you can represent with a point. So this is one of the ones where it probably makes sense to just look at the point A, but we'll draw the whole thing. So there's A. I do know it weighs 101 pounds. I do know that it has some amount of tension at angle beta. Oh, no, theta. I know that. We'll call that just T, representing the tension in cable AB. I see a new question in the chat. I'll get to that one once we do some work on this. This is not the entire free body diagram, though. I also have this force. We'll call that one the normal force for A. This force is, I need to figure out, what angle is this thing at? So this is the reaction of the ball touching the triangle. And the problem doesn't explicitly say to ignore friction, but it also doesn't give us anything like a coefficient of friction. So if you're not given a coefficient of friction, then assume that you're supposed to ignore friction. So this normal force is perpendicular to a tangent line at that point where they touch, where the ball and the triangle touch. That tangent line happens to be that line. And so I know that the normal force at A, I guess I used a capital A, I know the normal force at A is on a surface that is 31 degrees from horizontal. That's what alpha is telling me. So perpendicular, if I have a vector that's perpendicular to something that is 31 degrees from horizontal, the perpendicular to that is 31 degrees from vertical. So this guy is 31 degrees. So now I've got a setup here that, okay, well, I've got a free body diagram. The problem with it is it's a 2D concurrent force system. And for 2D systems, I have two equations. That's fine. Two equations means I can only solve for two unknowns. And I have three. I have t, theta, and this normal force at A. So that kind of throws things off. So we draw another free body diagram. Let's scroll down here and draw B. B, I know there's 21 pounds here. I know there's a cable force. I've already labeled it on one end as T, so this will just be T also. Also theta degrees from horizontal. And also there's a NB, the normal reaction force from the ball touching the triangle. I know that it's on a surface that's 59 degrees from horizontal. So the perpendicular to that is 59 degrees from vertical. I've got the same problem. I've got summation of forces in X equals 0. Summation of forces in Y equals 0. I've got two equations, but three unknowns. Another thing I could do, and this is where you probably could take it from here, is the two of these free body diagrams, I've got four equations with four unknowns. So I could solve that. I've got T and theta, that's in both of them, and I've got NA and NB. So that's four unknowns, and I've got a total of four equations. Summation of X and Y for your free body diagram 1, and X and Y for free body diagram 2. So I would have four equations, four unknowns. That'd be one way to approach it. Another thing you could look at, is there another thing you could look at? You could keep A and B together. Yes, so another way you could look at it is this. There's A connected to B. B weighs 21 pounds. A weighs 101 pounds. Got this same issue here with the normal reaction at A, 31 degrees from vertical. And I've got the reaction at B, 59 degrees from vertical. But what I don't have, if I make this the free body diagram, what I don't have is I don't have the tension to deal with because the rope is intact. I haven't cut the rope open, so I can't see the tension in the rope. So this diagram by itself, I can write summation of forces in X for that diagram and for Y, two equations. I've only got two unknowns, NA and NB. So this is not a concurrent force system though, so it does create some other issues, but I think they would be fine. We don't need to know about them right now. So you could do that and solve for NA and NB, and then take those values to free body diagrams 1 and 2, and then once you know NA in free body diagram 1, you can calculate T and theta, and you've got everything. So I think this one is a exercise in recognizing that free body diagrams can be individual objects or groups of objects or partial objects. In this case, you use individual objects for 1 and 2, and then if you did 3, that's groups of objects. And each one creates a new set of equilibrium equations. Each free body diagram you draw creates a new set of equilibrium. They're not redundant equations, so you can use them in a system of equations. So try doing some of those methods to get the problem 7 to work. The other question, problem 3, part 1 worked, but web work. Oh, okay. So let's look at problem 3 just to see. Some of these issues are web work issues. So let me see what. So that's this problem. So sometimes what happens with web work is that it is very particular about decimal places. One of the things I said on maybe the first day was that in engineering, you are usually using like a judgment call to figure out how many decimal places are measurable and usable for that instance. But web work isn't like that. Web work's not an engineer, it's a mathematics program, and it just uses as many decimals as it can calculate. So it could be a rounding thing, and it could be that maybe the way you calculated F2 was close enough to what web work thinks, but not close enough for the angle. I'd have to look more particularly. Whenever you run into one of those where you've done stuff right and then it starts falling apart, it could be something rounding. The best way to do that, if you can't find the solution on your own, best way to do that is to go back to web work and scroll down to the bottom, and it says email instructor. And what that'll do is it'll send me an email of your exact problem with your numbers in it and your answers, and I can look and see if it's just a rounding problem or if it's a calculation problem, like you've done something wrong versus it just rounded wrong. So that's particularly when you have part of the problem correct and part of it not correct. A lot of times that can be a rounding thing. So the best way to address those is to go into web work, email instructor, and just let me look at the actual problem numbers. All right. We will be back tomorrow, actually, right? Because we do Monday, Wednesday, Thursday. So we'll be back tomorrow, and we'll do... we'll talk about more stress. We'll add in this idea of strain. And today we talked mainly about things failing by yielding, but it could just be that they stretch a little bit, and how much do they stretch? Or how much do they compress? So we'll talk about that. That's strain. So we'll be back tomorrow, 12 o'clock. And let me know if you have